talk about. But then I realized that that was really unrelated to the workshop topic. So I changed my mind, and I'm going to present today some things that are not as new as the thing I was thinking about in the very beginning, but that are related to the topic. So this is kind of a presentation on something I did during my PhD thesis when I was in Saint-Etienne. So yeah, we'll use surrogate models to do some sensitivity analysis. So yeah, there might be some typos in the slides because I prepared that over the past day, yesterday night, and I actually finished some of the things this morning. So yeah, sorry for that if you can find any. So here we go. So the context of the talk is about getting an insight of what's happening into functions that depend on more than two parameters. So if we have a function that have a small number of input, like 1 or 2 inputs, it's very easy. We can print the function or at least make some graphical representation with just a few points and try to get an insight of what's going on. Now, as soon as we have a function with more dimensions, we can't plot the functions anymore. So we are kind of in trouble. Just to answer a very simple question like, what is the effect of the first variable? Does this variable has an influence on the output, or does this subset of a few variables have there interactions between them? So we are going to see a few methods to be able to understand the structure and to answer these questions. So I'll be using this very simple test function during the talk. So I see that as a function of 6 variables. So you can see there are only the first 5 variables that appear in this formula. So the 6th variable has no influence at all on the outputs. And then we can see we have something with an interaction between the first 2 variables, and then something additive for the 3rd, the 4th, and the 5th variable. Okay, so that's the very, very simple function we are going to look and on which I will illustrate all the examples. So the first thing to do is we can make some calls to the function. So I took some points randomly on the input space, and I compute the output, and this is what I obtain. So that's not very clear on this graph. So we can say, oh, maybe we have some trend on this direction, but yeah, that's not that much output. We don't really know what's going on. So another thing we can do is, so we are in our 6-dimensional space. We fix all the variables at one point, and then we make one of the variable to change. Okay, so we change one variable one at a time, and then we can make some plots. So here all the variables are fixed at the center point of the domain, and then I will make the first variable change, and that gives me an idea of what's going on. I can also use these kind of plots to get an insight on the interaction between variables. So here I'm plotting the function as a function of x1, all the other variables being fixed, and between this curve I just change what is the value of x2. So if I want to make a small graphical representation of that, I just say this is my space with x1 and x2, and I'm plotting a function of x1 for different slice of x2. So I'm basically looking, how does my function look like in there? So since the function in x1 changes when I change x2, that means I have some interaction between these 2 variables. On the other hand, if I look at how does the function as a function of x4 changes with x2, I just have a translation, so there's basically no interaction between these 2 variables. Okay, so that's a first thing we can look at. But we are now going to see tools that are a bit more precise and that more helpful. So a common representation of a function, if you want to study its internal structure, is this decomposition. So it has many names. It can be called the Fanova representation. It can be called the HDMR for high-dimensional model representation, the Sobel decomposition, the Evding decomposition, the Sobel Evding decomposition. Okay, so depending on the literature, there are lots of names for that. So the idea is to write our function as a constant plus some functions that change in only one direction, plus some functions of one variable, plus some functions of two variables, and so on. So we get a decomposition of the function with some increasing interaction term. There are actually many representations of the function like that, because, for example, we could say, oh, I'm going to put one part of the constant here in one of these functions over here. So I would obtain another representation, but that is not as meaningful as if we make sure all the constant term is in this one, all right? Because then if I'm wondering what is the constant term in this function, I just have to look at this guy. Similarly, we want this term to encapsulate all the variations that can be explained only by f of one variable, okay? So this will get all the variations that can be explained by only one variable. And this will be just the second order interactions and so on. So when we are saying that, the conditions we actually want is to have an orthogonality between all these functions. So we are going to project our function f onto a lot of subspaces that are orthogonal, the first one being the constant function, the second one being the functions of one variables, and so on. So, as I say, if we want f0 to encapsulate all the constant components of f, then we want all the fi to be zero mean. And similarly, we have this kind of property for all the other terms. And another way to think about that, as I said previously, is we want all these terms to be orthogonal. Any question on that? Okay, so if we impose this condition of orthogonality, or the one that the constant term encapsulates all the constant components, there's actually one unique way to decompose the function. And this is the term we obtain. So f0 stands for the constant term. f1 of x1, we integrate f with respect to all the variables except the if one. And we have to subtract the constant term to make sure these two are orthogonal. And so on, we have all that. So this will be the constant term. This will be called the main effect. These will be the interactions of all the two, and so on. We have a whole decomposition of the function. If you want to know what is actually the effect of the first variable, we have. So if I want to plot, I want the best plots of my function that is high dimensional as just a function of x1. I will actually need to add these two terms, okay? So that can be seen as the total effect of one variable or the total effect of one subset of variables. So that would be to sum. If you have a few variables, you need to sum all the terms for these variables included in there, right? So if we come back to our test function, this is what we obtain. So we have x1 and x2 that have the same effect. So it's normal, because if you remember the definition of the function, it was the sine of x1 times x2. It has to be symmetric with these two variables. And something quadratic for x3, something linear for the two others variables, and nothing happened for the last one. Okay, so using this decomposition, we can see what's going on inside of the function. It's a way to open f, that is, to open the box and looks what are the elementary bricks f is made of. We can do the same thing for the interaction terms. So that's the interaction between x1 and x2, and that's the interaction between two variables that do not interact. Okay, so we really get an insight of what's going inside this function. So, and if I'm wondering how can I plot my function, what would be the best plot to show my function just as a function of x1 and x2, I just have to sum my constant term, what's going on in x1, what's going on in x2, and the interaction between these two variables. All right? Yeah. So if we come back to the expression of these terms, we see that they depend on integrals. Okay? If we are a bit limited in the number of evaluation of our function because it's costly or because we don't have that much time, then it means that we can't really compute all these integrals. So the idea would be to get an approximation of what we've just seen, but using much less evaluations of the function. So some models will be very helpful because they will have a structure that is easily to interpret. For example, if I look at a linear regression model that just depends, so let's say we are studying a function of just 2 variables, I make this prediction with a linear regression model, then it's very easy. I just have to look at the coefficients and they will tell me things about what's the value of the constant, what is the effect of x1 and the effect of x2, basically by comparing beta 1 and beta 2 if the two x's are of the same range of variation. Okay, so for some model it's quite easy, but it can very easily become more tricky because, for example, if I start adding an interaction term, I'm not sure that all the effect of the first variable will be in B1. Some of them maybe will also be in this coefficient. And similarly, some of the constants may also be included in this term. So this decomposition of the model, it gives an insight, but it does not have exactly all the property we wanted from the van der Waal representation. So now we are going to look at particular models that do satisfy all the things we need. One more word. So we just said that linear regression model, they are usually quite easy to interpret because you can look at the value of these coefficients and get on each side of the effect of the variable, depending if beta is positive or negative or so on. Now, if we look at Gaussian process regression model, the way we usually look at them is like that. We see our model as a linear combination of the observations we have, all right? So that's the statistical point of view, that when you look at this model as the best linear unbiased estimator. So you look at the best linear combination of our observations. There's an alternative point of view that is the Rhs Framework, so the reproducing kernel Hilbert space framework, where we look at what would be the best combination of these basis functions. Okay, so the model is a product, a matrix product with a vector, a matrix, and another vector. Now, we can see this model the two ways around, either as the best combination of f or as the best combinations of this guy. So now this looks like a bit like linear regression. I'm making a prediction that is a linear combination of basis functions. But since these basis functions have this shape, usually they have the shape of the kernel, so it's usually a function that is kind of a hat. It will be quite difficult to interpret the values of these coefficients over here, right? So the model is more like a black box function, and we are not really going to say, oh, the value of my covariance matrix times the f, I obtain these vectors, so I have a big coefficients here, that means something I can interpret. No. The basis functions are local things, and it's not easy to get an insight of what's going on inside. So, okay, some models like the Gaussian process regression model are not that easy to interpret if you use the usual ones, and we are going to see in the talk that actually it's if we choose the appropriate kernel, then it's very easy to get an insight of what's going on. So I'll say a few words about polynomial chaos before talking about GPR. So the principle of polynomial chaos is to get an orthogonal basis of polynomials that will satisfy the properties we are interested in. So a common basis for polynomial is to take the constant x squared, and so on. So if we want this basis to be orthogonal, so we are going to take the first function, x, and we divide it by its norm. Then we are going to take the second, the constant and divide it by its norm. Then we are going to take the second basis functions, and we are going to make sure we make it orthogonal to the first one, and we make sure it's normalized, and so on. So this will give us another basis that will be an orthogonal basis. And we do have the orthogonal property we were looking for, which is that this function is orthogonal to this one. So this is in the one-dimensional case. Now, we say we were interested in higher dimensional functions. So we just can take these bases and we make tensor products between these bases in each direction, and this is the kind of thing we obtain. So when I use here inner product, I don't specify what inner product I'm using. So I'm using the L square inner product, the usual one, and this inner product is defined for a given measure. So now if we change the measure we use in this inner product, we will obtain different bases of polynomials. So for example, if we take a uniform measure over one-dimensional input space that is given by -1, 1, this is what we obtain when we do the orthogonalization of the usual polynomial basis. If we take a Gaussian measure over R, we obtain another family of polynomials. So this is basically how they look for the Legendre basis. We have our constant function, then we will have something linear, but that is orthogonal to the first function, and so on with increasing degrees. And now if I make the tensor product between the elements of this basis, this is my new basis of polynomial. So I have a constant, I have in blue here functions that will depend only on the first variable, then here functions that will depend only on the second variable. I will have interaction, and I keep increasing the order to get more and more basis functions. So now if I use this particular basis to do some linear regression model, we'll see that the model we obtain has some very interesting properties. So our model basically writes like that. It's a linear combination of our basis functions. So if I want to compute what is the Fanova representation of my model, so the first term, it's just the integral of my whole model. So I'm going to integrate M with respect, so here I'm only taking a two-dimensional example to make the expression not to explode. So the first term is the integral of M. So if I compute this integral, I know that all the terms here that are not equal to h00 have a zero integral. So this integral is all the terms in the sum disappear except this one. And now I know that the integral of h0 is equal to 1 because it's a normalized function. So I just end up with the term beta 0, 0. Now if I want m1 of x1, a similar thing happens. I have to compute this integral with respect to x2. I know that the only functions that do not depend such that this integral is not equal to 0 are the one in 0, 0, and the one in 1, 0, and the one in 2, 0. So as previously, all these functions are normalized, so I obtain something that is very simple. So just by choosing the appropriate model that is based on basis functions that are already orthogonal for the measure we are working with, we have directly this decomposition of it, so we don't have to compute these integrals. They are already computed because we did that in one dimension on the basis we are interested in. Okay, so we can see this expression that was depending on very high dimensional at the very beginning is not very straightforward just because we did these integrals in one dimension at the very beginning, and we use that when we compute our model. Do you have any question on that? No? So this is what we obtained on the motivating example. I think I've been using 60 points in here, which is really not much in 6 dimensions. And we can see there are basically two curves overlapping here, the black one and the red one. And the red one is the truth, and the black one is just our estimates using the polynomial scale regression model. So yeah, we can end up with just a few observations. We can end up with a very good approximation. And this is because the function we are studying is actually quite simple. It's over 6-dimensional input space, but it actually depends just on the sum of these 5 terms plus 1 interaction. So it ends up being quite easy to learn. And one more thing, to obtain this figure, I've cheated a little bit because I've included exactly the basis functions I needed to approximate the function f. So usually you don't know exactly what basis function do you need, so you will add a few extra, you will be missing some of them, and this is more typically the thing you will obtain. Here I've ignored that there is some interaction between the first and second term. So my model is a bit misspecified, and I'm still able to recover something that makes sense. The term that will be very wrong will be the prediction of the interaction according to the model, because this will be flat because it does not have this degree of freedom, and whereas there's actually an interaction between these two variables. Okay, so still with a few points we can end up with something with having a good idea of what's going on inside the function we are looking at by choosing the appropriate basis when you do linear regression. The thing is, we've been using basis of polynomial, but we all know other bases that are orthogonal for the usual L2 inner product. For example, if you take the constant and some sines function, the sines function will have 0 mean, and then you can do the exact same trick we did here. It's not specific to polynomial chaos. Okay? To do that, you just need a basis of orthogonal functions such that the first term is equal to the constant function, and then you can do all these again. So now we are going to talk about Gaussian process regression. So one of the things that is great about Gaussian process regression is that we don't have to choose the basis functions we want to work with, or we don't have to choose the actual order we want to work with. And so that makes things simpler. On the other hand, we have to choose a kernel, but my point of view is that it's easier to choose a kernel than to choose a set with many basis functions. And yeah, and we also like all the confidence intervals and all the posterior distribution we obtain with this kind of models. So we are going to do something quite similar to what we did in polynomial chaos. Instead of doing that in a finite dimensional space, because we have a finite number of basis functions, we are going to do that with GPs that are spanning an infinite dimensional space. So the first idea, if we want to get a model that has kind of the structure we want, so to write as a constant plus a sum of univariate function plus a sum of bivariate functions, is to look at ANOVA kernels. So if you remember the thing I was saying on Monday, this is a valid covariance structure, because what are we doing? We are summing kernels, and we know we can do that, and then we are multiplying the kernels we have just summed. So we know this will be positive semi-definite. That's straightforward. Now, if I expand this product, I will obtain this kind of thing. So that's another way to look at the kernel. Instead of having a product, I have a sum, and when I have a sum of kernels, I know I can interpret that as the covariance of a sum of Gaussian processes. So this process, how do they look like? So this one will generate constant sample path. All right. These guys, they only depend on, well, 2 variables, but only one direction. So they are associated to one-dimensional GP. And then we have second-order interactions and so on. So we take our initial process with this kernel, and we can look at it as a sum of functions with increasing interaction order. So that's very similar to the Fanova representation I was showing before. But there's one condition that is not satisfied, is that these are just samples from these kernels, and even if we choose this process to be 0 mean, it does not mean that the samples, if I take the integral of a sample, I will not have exactly 0. I will have something that will be centered on 0, but with some variance. Now, if I use this kernel to do some Gaussian process regression, I can again, I have my usual model. I can specify that this term is equal to a sum of kernel. I can expand with respect to this product, and I obtain something here that do not depend on lowercase x. So this will be my constant. Here, terms that depend on only one variable. So this will be some univariate models, and so on. The thing is, as before, this looks like the Fanova representation of M, but it is not, because this function is not 0 mean, or yeah, let's say these functions over here are not 0 mean, so they do not satisfy the orthogonality condition we were interested in. So if we want to have sample paths that have exactly 0 integral, it's a bit like saying I want a sample path that goes through this point. Okay, we know that we can. If we have one observation, we know that we can make a Gaussian process that will interpolate. So we have a conditional distribution that will interpolate this point, right? No, we don't have the information that z at a given point x is equal to I don't know a given value, the thing we have is that we know that the integral of our process equals 0. Okay, so that's very similar to the conditioning we had before. Instead of conditioning with respect to the value of the process, we condition with respect to the value of the integral of the process. So I'm going to look at this new GP that is a conditional distribution of any GP Z. So we have very low conditions, not restrictive conditions for these to be well defined. We just want basically this integral to be finite, right? So we just want to say, okay, so we are working on a compact, and we just say, so basically we just want the variance of this to be finite if we are working on a compact. So we define a new GP that has the distribution of Z given that the integral of Z is equal to 0. So if you remember the usual formula we have for Gaussian process conditioning, so it's a product of three terms. The first one is the covariance between Z. The first one is the covariance between Z at the point x. So this is where we predict the mean, Z at the point x, and this integral. So this covariance can be seen as an expectation because our terms are centered, and then we just flip the expectation that is an integral with this integral over there, and we obtain this term. Okay. The second term is the covariance matrix of this one. So here we just have one random variable. So this covariance matrix will actually just be a scalar. So the inverse of the variance of this quantity, which is this, times the value condition, we have 0. So our mean will be scalar divided by a scalar times 0. Now if you look at the covariance, it's the same trick. We cover the covariance between these two guys, then the product of matrix with this covariance and this, the inverse of this variance. So now I have a new distribution that takes into account the fact that the sample of Z of Z0 must be exactly 0 mean. So that's another way to write the thing. And now if you compute the integral of Z, you will obtain exactly 0, okay? Because we condition the process to have 0 integrals.
Do you have to specify the region which you're
yes.
taking this sample, right? Because
yes.
Obviously, go a little further.
Yeah, right. So I was saying I'm working on the compact subspace. I'm pretty sure that it will still work if I work on R, but I have, for example, a Gaussian measure on R or something like that. You either need boundaries or you need your process to be integrable with respect to the thing.
When you further do sensitivity analysis with this, like in a second, I assume you probably will, you need to know what sort of Rhs you are interested in sensitivity.
Indeed, yeah.
Okay.
Okay, so now we can take the ANOVA kernels I was talking about before, just replace here. We were using any arbitrary kernel. Now we specify we want a kernel that has sample such that the sample will be 0 mean. I have the same decomposition as before, so I can associate a similar decomposition of the GP, but now all these terms are designed to be exactly 0 mean. So this is the FANOVA representation of my process that I can get directly, because now I can sample directly from this guy by using this covariance function. And it comes with no extra cost. We just need to be able to compute here these low-dimensional integrals. Okay, this is a one-dimensional integral, and here a two-dimensional integral. And knowing this in one dimension allows us to, by making the product of covariance function, to obtain a covariance function over the whole space. So this is what happened when I look at sample path from my GP. So here I have Z that is not centered, because in Z there's a constant component that is centered around 0, but the actual value is not exactly 0. So here I have a shift, and this process is the sum of 4 processes. The constant one, something that changes only with x1, a function only of x2, and then a process of the interaction between these two variables. Okay, so all these have interesting property. For example, if I were to take the integral of this function on any of the on any subspace here, I would obtain exactly 0. The same thing here, if I were to take integrals in any of the direction for any fixed variable, I will also obtain exactly 0. Okay, so I have some very good properties for this. So once we have this structure for the kernel, then our Gaussian process regression will have directly the decomposition of the mean, the Fanova representation of the mean. So as before, I explained with respect to this first term, I obtain this sum, and this sum will satisfy all the conditions we want. Another interesting thing is when you look at this sum model, for example, so that will be k0 of x1, x1 times the inverse of this matrix times f, and this can be interpreted as a conditional expectation. So it's the conditional expectation of, here I took the example of Z1, given the observations of the whole process Z. So that looks like a noisy Gaussian process, the prediction of a noisy Gaussian process, because I want to predict something, given I have observed these things I want to predict, plus some observation noise, right? The observation noise being not something just one value on the diagonal, but being some correlated noise, so a noise with a covariance structure. So since we have this interpretation of the submodel as conditional expectation, then we can also associate prediction variance to our submodels, and being the conditional variance of the die given this quantity. So this is what we obtain on the example. So yeah, the model here is not perfect. It's a bit how could you criticize this model? What would be a bit wrong if I compare the true value and the predicted one? It's a bit overconfident. Okay, we can see we are far away from our 95% confidence interval. So this model is not perfect, but at least I have a model, and it's very easy to look at what's going on inside and what are the elementary bricks, and that comes with almost no computation time, because the first integral we have to compute, we can do that analytically. You do that once, and then it's very easy to focus on some of the elementary bricks your model is made of. And this is what we obtain for the interaction between the first and second variables. So once again, we have confidence intervals over our prediction of the interactions. So now how can we use that in sensitivity analysis? So yeah.
Just about the normal kernels, because the normal kernels are a very specific interaction, right? Basically, the product of two covariance matrices, does that imply any type of function families they can produce? Because I guess it's like mature kernels cannot be generated by multiplication of the two kernels from two dimensions.
Yeah, you're right. So you can actually take two Mattern kernels and you multiply them together, but you will not obtain the same Mattern you have with using the distance between the 2 points. So that's something that is very true, for example, for the exponential kernel, because that will really change the shape of your sample path and of your assumption, because you're losing, well, the covariances decays much faster on the diagonal than it decays along the axis. But if you consider other kernels, like the squared exponential kernel, then it ends up being the exact same thing. So when you increase the order of the kernels in the Mattern family, it makes less and less difference between taking a product of kernels and taking the actual kernel depending on the distance. So you're true. We are making some kind of assumption here by taking the product of kernels, but as long as the order of the Mattern is not that small, or if you're working with the squared exponential kernel, you end up with the exact same thing. Yeah?
What, can you do it with all kernels? Because you need to be able to do a double integral over both x's.
Yeah.
Right?
So yes. So I did it for the squared exponential kernels, and for the Mattern you can do that too using integration by parts. So yeah, you end up having the expression. It's a bit well, it requires a bit of time and some
so you can do the integral
some
over
paper.
both x's and Mattern.
Yeah. Yeah, you can do the integral with respect to one, and then you just have to integrate that once again. So remember, we are working on one-dimensional kernel. Okay, so it's a product.
Yeah, you got products.
Yeah. So in the higher dimension, you have products, and you just have to compute. Yeah. For in one dimension, you have one double integral to compute. But yeah, that,
and then
you can have it.
Of that with a double, which it doesn't say.
Exactly. Yeah. So the idea of sensitivity analysis is to try to quantify the thing we were looking at. So what would be the influence if I have variations in my output? What would be the variation of the output? So in other words, it's how the input influences the output. This is what we want to study. So we can do that locally. So we say around one point. So for example, around the optimal point, if we are interested in minimization, do my variable influence the output? So that's something people do a lot in robust optimization. And I'm going to talk more about global sensitivity analysis. So if I have some uncertainty on my inputs, how do that make the outputs uncertain, and try to understand this relation on how much each input or each subset of inputs acts on the outputs. So yeah, that's basically the point. If we introduce some randomness in the output, how random is the output? So we are going to focus on global sensitivity analysis, and more precisely on global sensitivity analysis using variance. So it means to quantify the randomness of something, we are going to look at its variance. So if we have now a random vector over the input space, and we will assume this particular structure for the distribution of our random variable, that its probability density factorizes. So basically it means that the input in each dimension is independent, right? So if we have this structure for mu, then we can build our Fanova representation using mu as the measure over our space. And so this is unique, and now it's quite interesting when we plug a random variable in there. So I'm going to evaluate this for a random value of the little of lowercase x. So if you look at all the fi, they are centered and they all are independent. So we have all these properties just by the property we have for the orthogonality between the terms of the decomposition. So the orthogonality we are talking about in L square here implies the independence between our random variable. Actually, they are not independent. They are not correlated. That would be more precise. Yeah. So since they are not correlated, then if I compute the variance, then this variance writes as a sum of all the variances. So the definition of the Sobel indices is that the Sobel index associated to one variable or one subset of variable is equal to the variance of one of these terms divided by the total variance. We know the variance is positive, so it means that this quantity has to be between 0 and 1. And by construction, this is the sum of all these variants. So the sum of all the index will be equal to 1. So you can look at one of these index as the proportion of variance that is explained by one variable or one subset of variables. Okay, so you can estimate these quantities with Monte Carlo methods, but that requires a lot of observations. So you can do that if your function is costly. And of course, we are going to use the model I was just talking about, for which we have an easy representation of the Fanova decomposition. So in the case of polynomial chaos, then, so if I'm just looking at the numerator of the Sobel index, it's the variance of a conditional expectation. They all are independent except, so hi is independent of these except this particular one. So we end up with these variants, we end up with beta I squared. So once again, we have no computations at all to do because we started with the right basis. And yeah, so we have some very simple expression for the Sobel indices. This guy has worked a lot on this kind of thing. For Gaussian process regression model, we have something very similar. If we take the right covariance function, the one I was talking about, then we have this expression for the sensitivity indices. So this is just a product of matrix. We have one more integral to compute compared to what we computed before, but it's a one-dimensional integral, nothing impossible here. So, okay, it looks a bit ugly, but it's just linear algebra, and you can compute that very, very easily. And the great advantage of this compared to polynomial chaos is that we have an infinite dimensional space we use to approximate our function. So for the sensitivity analysis, if I compute my indices on the test function I was talking about at the very beginning, so this is what I obtained. So I just made two models here with two different design of experiments. I was a bit unhappy because my first model was returning the exact values I was looking for, so that was not really fair. So I ran this again with another design of experiment, so 60 points, Latin hypercube sample with maximum criterion. I obtained a slightly different design, well, a different design and slightly different indexes. But yeah, basically we are able to recover very well the things we are looking at just using a few observations of the function. So at the conclusion, so there are interesting tools to try to get inside functions that are high dimensional to understand the structure of what's going on. I think the HDMR representation is very interesting for this. Quite often when you have a lot of input variables, then the actual dimensionality of your problem is lower because some of the variables don't have any influence or just a small influence on the output, so that can be ruled out. So to compute the sensitivity index, you can do Monte Carlo, but if you have a limited budget evaluation, then you can go for model-based approach. Some modeling tips. When building a model, it's important to think, what am I going to do with this model? If I know I'm going to do some sensitivity analysis, here I was showing that we can choose a model that will be dedicated to that and that will have the properties we want to make all the computations later much easier. And another point is that it's possible to include more fancy observations in GPR. So here we are conditioning a GP with respect to the value of its integral. You can do the exact same thing and do some conditioning with given the value of the derivatives, for example. So this is the talk when I finished yesterday night, but I was a bit cross because the workshop is about uncertainty quantification, and here I'm not doing the thing right because I'm doing all my uncertainty quantification of the mean of my Gaussian processes, which is not really what you want. So my Sobel indices are deterministic for a given design of experiments, whereas I have some uncertainty in my model. So I really want to do the things properly. You really want to account for the uncertainty you have in your model, and that should make some uncertainty also on your Sobel indices. So I added one more slide this morning, but I had to write some code to do that. It's actually what happened if we look at the sensitivity indices directly on the sample path. So as previously, if you have the right covariance function for Z, so the one I was talking about earlier, then it turns out that this quantity, so the numerator of the Sobel indices, can be computed quite easily because here you have independence between these that you can use. So we know that this conditional expectation will just be this quantity, and now we just have to compute the variance over x of this quantity. So this will still be random because we have some randomness in that is not squashed out by the variance. So if you do that, you recover the variability of your indices according to the variability of your sample path. So this is just for prior distribution. So I took a two-dimensional GP. I basically sampled from it and computed all the sensitivity indices on the sample path. The particular structure of that allows me to do that very, very straightforwardly. I just have to say I take a sample in quite a lot of points, and then I compute the variance of the values observed of this sample. So this has and this is what I obtained. So the two effects for the distribution of the Sobel indices for S1 and S2, and the distribution of the Sobel indices for the interactions. So now I was running out of time, so I couldn't do the same figure for the posterior distribution. It's a bit more tricky because for the posterior distribution, these quantities here are not independent anymore. Okay, if we look at the the predicted covariance of a GP, then you will have interaction between these guys. But still, you have the orthogonality around x for your conditional, the orthogonality for the variable x for the decomposition you're looking at. So you still can do the same trick as here and get the distribution of your Sobel indices, right? So that was how to do properly the UQ for these things, taking into account the variability on the samples. Right, I think I finished. Any question? Yeah. Yeah.
Where you typically need, great advancement is that you typically need, for a high-dimensional problem, so like 50 inputs, you merely need like, say, 100 runs of your simulator, whereas with the emulator you might need like 150.
Yeah.
So do you want to comment about those methods and
yeah.
whether you've looked at them or whether you
So the thing is, generalized additive models are very helpful when you have a lot of inputs, because basically if you have a budget that does not grow exponentially with the number of inputs, then you can't cover the space anymore, so you can't do anything. But if your budget is linear, you can do anything properly except additive models. So if you want to fit an additive model, and you still can use, so if you want to use this property from additive models, you still can use this kind of process, just instead of assuming ANOVA covariance structure, for which you will have all the interactions between all your terms, you can just assume a sum for your kernel that will be 1 plus univariate process with 0 mean. And if you do that, you will recover a GP additive model, and then you will benefit from both. So you can compute all your things very, very easily. You can compute the variance of your Sobel index according to the uncertainty you have in your models you're training. And and you benefit from the generalized additive model because you have an additive covariance functions, so your model will be additive, right? So you don't need many points to train your model. So you can actually get the best of both just by getting rid of, not considering an ANOVA structure for your kernel, but just an additive structure, depending on one variables. Yeah.
So for the ANOVA representation, you have this construction where you could basically construct each of the representative functions by taking these rows and
Yeah.
constructing the previous functions.
Yeah.
So since all of those are linear operators, could you just take a GP defined over where you haven't done any, where you're not using the ANOVA kernel,
Yeah.
the ANOVA kernel, and just do Bayesian quadratures, like integrate things out, or would that play out?
Okay, so that's a very interesting point. I think if you do that, so the way you construct your kernel, so you want basically to take your process, you project that over the constant function, and then you using the L2 norm, and then you subtract that to your process, and that will give you a process that is zero mean. Right, so that's your idea. So you take a usual kernel and then you write it in the appropriate basis. The thing is, if you do that, if you use the L square operator to do that, then you will not have independence between your constant term and the term that is zero mean. So you can either choose to ignore the fact that these are not independent, and then it will have some strange effects on the boundaries. Another point of view to the thing I was presenting here is to consider the projection of a GP over the constant function, but not for the L2 norm, but for the RKHS norm. And that will give you the exact zero mean process I was talking about. And this is actually the right way to project your process onto the zero mean function. That can be interpreted as a conditional expectation. If you do what you were talking about, then you will have the same kind of structure. You can use that to do exactly the thing I was doing, but that's not the best way to do it, because you're not orthogonal. That's not a conditional expectation. But still, you will retrieve some very similar results. There will be some weird things going on the boundaries of your domain. I'm pretty sure I can find some figures if you want later.
Okay, if there's no other questions, we can also talk to Nicolas across the break and